You know that feeling at a concert when a deep bass note seems to vibrate through your whole body? Or when you're pushing a kid on a swing and you get the timing just right to send them flying higher and higher? Well, that powerful, sometimes kind of startling feeling? That's resonance. It's this fundamental principle of physics that honestly shapes our entire universe, from the music we love to the light we see. And today, we're going to see how this one idea connects some pretty wild things.
Right. So what on earth does a kid on a swing set have to do with a giant collapsing bridge? I mean, on the surface, they couldn't be more different, right? One is this simple, happy childhood memory. The other, well, it's a total catastrophic failure. But the answer to what connects them is the exact same powerful phenomenon, resonance. We're going to dig into this hidden rhythm and uncover a really surprising twist in a story that, let's be honest, almost everyone thinks they already know.
So, let's start with something we all get right away. The playground swing. Every single swing has its own natural rhythm, a specific time it takes to go back and forth. If you want to go higher, you can't just push whenever. You have to time your push perfectly with that rhythm. It feels totally second nature, but what are you actually doing physically? Okay, hold that thought about the swing for just a second. Now, look at this. A massive steel bridge, literally twisting like it's a ribbon in the wind just before it completely tears itself apart. This is where we're headed. But, believe it or not, to really understand what went so wrong here, we first have to master the physics of the playground. So here's the key idea. Everything, and I mean everything, from a guitar string to a skyscraper, has what's called a natural frequency. It's the speed it wants to vibrate at if you disturb it. Resonance is what happens when you start applying a force at that exact same frequency. With each push, the object just soaks up the energy, and the vibrations, the oscillations, they just get bigger and bigger and bigger. And, there are basically two ways to do this on a swing. The most obvious one is forced resonance. That's when someone is pushing you. It's an external force matching the swing's natural rhythm. But then there's what you do when you're by yourself. You pump your legs. That's called parametric resonance. By shifting your weight at just the right moment, you're also adding energy to the system. In both cases, the secret ingredient is timing. It's all about matching that natural frequency. But the swing is just the warm-up act. Once you start looking for resonance, you see it absolutely everywhere. It's not just some neat little physics trick. It's a fundamental force that can be used to create amazing things or unleashed for total destruction. And you can really see the two faces of resonance here. We use it for good all the time. When you tune a radio, you're matching a frequency. When you play a guitar, you're using resonance. Even lasers work on this principle. But that exact same principle can be incredibly destructive. A singer's voice can literally shatter glass. It can cause dangerous swaying in rocket engines, and, as we're about to see, it can bring a massive bridge crashing down. Which, of course, brings us back to that bridge. The collapse of the Tacoma Narrows Bridge is the classic, textbook example of resonance gone terribly wrong. It's the story every engineering and physics student learns. But the real question is the story we all know the whole story? So this bridge had problems right from the get-go. It was incredibly long and narrow for its time, and almost immediately after it opened, it started doing this weird up and down wave motion in the wind. People actually nicknamed it Galloping Gertie. For about 4 months, it was this quirky local tourist attraction. And then, on November 7th, in what was just a moderate wind, that galloping suddenly turned into a violent twisting motion, and the whole thing just tore itself apart. Now, this is the explanation you'll find in pretty much any physics textbook. The idea is simple. The wind was providing these rhythmic, periodic pushes, kind of like someone pushing that swing, that just happened to match one of the bridge's natural frequencies. So the bridge absorbed all that energy, the twisting got more and more out of control, and boom, collapse. And when you look at this footage, that simple resonance story, it feels right. It makes sense. You can almost picture the wind pushing it at just the right rhythm, making it twist more and more. It's a really compelling, easy-to-understand narrative. And for decades, it's what most of us were taught. But it's also not quite right. Okay, so here's where things get really interesting. This is where our story takes a very sharp turn. Because when you dig into the actual physics, you find a more complex and, frankly, a much cooler culprit than just simple resonance. The answer, according to some very detailed analysis, is a clear no. That classic story of the wind's frequency perfectly matching the bridge's frequency, it just doesn't hold up. So if it wasn't resonance, what in the world really brought down Galloping Gertie? The real cause was something called aeroelastic flutter. Now, this is a totally different beast from resonance. See, with resonance, you need an outside force pushing at just the right time. With flutter, the object's own movement through the air is what creates the forces that make the movement even worse. It becomes this vicious, self-sustaining cycle. The bridge was effectively powering its own destruction.
This table really breaks down the difference. With the resonance myth, you need these perfectly timed wind gusts pushing the bridge. But in reality, the wind that day was pretty steady. What happened was the bridge's unstable shape took the energy from that steady wind and converted it into that violent twisting. They call it self-excitation. The more it moved, the more forces it created to make it move even more. It was a feedback loop from hell.
And here it is. This is the smoking gun. The wind moving past the bridge did create these little rhythmic whirlpools of air. It's called vortex shedding. The old textbook story assumes that was the push that lined up with the bridge's frequency, but the data shows the frequency of those vortices was completely different from the frequency of the bridge's final destructive twisting. The numbers just don't add up. It couldn't have been simple resonance.
So at this point, you might be thinking, okay, resonance, flutter, tomato, tomato. What's the big deal? The bridge still collapsed. But this distinction is actually incredibly important. It's a distinction that has saved countless lives.
See, this isn't just about being nitpicky with words. Getting the physics right is literally what allows us to build structures that don't fall down. The lessons that we learned from Galloping Gertie's flutter, not its supposed resonance, led directly to the way we design aerodynamic bridges today. And it's absolutely critical for designing airplane wings that don't just tear themselves apart in midair.
So what's the big takeaway here? The famous Tacoma-Narrows Bridge collapse wasn't caused by simple resonance. It was aeroelastic flutter. And it's this powerful reminder that the simple stories we learn in textbooks can sometimes be a little too simple, maybe even misleading. In the world of engineering, getting that deeper truth right is what stops the next disaster from happening.
And that really leaves us with one last thought, doesn't it? The story of this bridge is this fascinating case of a common scientific myth being replaced by a more accurate, more nuanced reality. And it just makes you wonder, what other simple facts that we all take for granted might have a deeper, more complicated, and maybe even more interesting story just waiting to be told?